and welcome to 15.3 Heterogeneous Aqueous Systems. In this section we're going to take a look at systems where you have more than one phase. That's why the term is heterogeneous aqueous systems as opposed to the homogeneous systems which only had one phase. So the real difference here is the eye test. Can you see multiple phases in the system? If yes, you have a heterogeneous system. And one of those types of systems is what's called a suspension. A suspension is going to be different from a solution because the particles will settle out over time. Will settle out if left standing. Simply meaning if you take your container and just let it sit there, the particles will sink to the bottom. Now the particles here are relatively large. They're going to be greater than 1,000 nanometers. Nanometers are billionths of a meter, so these are still incredibly small particles, but compared to the size of atoms and molecules, they're much bigger than that. And so these things are going to settle out if left standing. Now, what you can end up doing is filtering out that suspension, as you can see in the picture off to the right. Something like muddy water would be a suspension. Other types of suspensions would be something like adding some type of cornstarch or something to thicken a sauce or a gravy when you're cooking. Other suspensions include antibiotics that are added to a particular solution. And I know when my son uses amoxicillin, it is a suspension. You have to shake that up because the antibiotic will settle to the bottom, and so if you simply pour the suspension out into the spoon without shaking it up, you're not actually getting the medicine that you need. Alright? So a suspension is going to actually settle out very large particles. Now, on the other hand, a colloid is going to be a system. Again, it is a heterogeneous system, so you can see the particles, but the particles are smaller. You're going to be on the order of 1 nanometer up to the 1,000 nanometers. And colloids do not settle out. Alright, so these things are going to stay in suspension, and you actually know a lot of colloids. You probably just haven't talked about them in terms of being called a colloid. For example, whipped cream, marshmallows, milk, mayonnaise, hairsprays, dust, paints, jellies. These are all actually colloidal systems. You call them by different names depending on what type of medium you're using to disperse a particular phase. For example, if you disperse a gas within a liquid, we call it a foam. Whipped cream and shaving cream is simply dispersing the gas throughout the liquid. That's why it's not just a liquid that runs all over the place, although it eventually can. It's still going to stay, somewhat together, as opposed to, say, a marshmallow where you've injected a gas into a solid, which is much more rigid. If you dissolve or disperse a liquid within a liquid, you call that an emulsion. Milks and mayonnaise are emulsions. You can also have certain types of skin creams. If you mix different creams together, they're an emulsion, depending on how you mix them together. Aerosols are where you disperse a liquid within a gas. As you pump your hairspray, depending on what type of hairspray you're using, that's actually a liquid that's being dispersed by the gas. Fog, clouds in general, those are going to be aerosols. And again, these are all colloidal systems that do not separate out based on their particles. Now, of course, milk and mayonnaise, they will start to spoil and separate, but that's not the separation of just the colloidal system. That's something different altogether that's going on. Similarly, you have solids that can be dispersed by gas or liquid. If you disperse a solid throughout a gas, you have smoke. Dust in the air is a colloidal system. Now, eventually that dust can settle out if you disrupt the colloidal system. Paints are in blood. Those are both colloidal systems as well, where you have solids dissolved, or excuse me, dissolved is not the word, dispersed within the liquid. Okay, so all of these are colloidal systems. Now, they all have two or more phases. Again, passing the eye test is what determines whether or not you're a suspension in a colloid or a colloid versus a solution. Another way that you can differentiate between those is by observing what's called the Tyndall effect. The Tyndall effect is the scattering of visible light and it's going to be scattered by colloidal particles. Now, if you look at the diagram below, notice that a solution will not scatter the light. It's because the particles are too small. A colloid will reflect and scatter the light out, but oftentimes you can't see the particles themselves, versus a suspension, which has larger particles. You can actually see those things moving around within the light. If you've ever seen a sunbeams, so you got the sun and you're in, say, a forest. Okay, there's the tree trunk or whatever. You'll see beams of light shining through the forest. Okay, that is the Tyndall effect, and it's usually happening because of the colloid that's in the atmosphere, which is a fog. Now, or it could be some type of dust. Oftentimes inside your house, as light passes through the window at a certain angle, you'll see that light beam going across the room. Well, that's because dust is probably floating around in the air. All right. Now, with a Tyndall effect, they actually observe particles moving around in a colloid, and they coined that term. This was actually by a guy by the name of Robert Brown. It's called Brownian motion. They actually determined that particles do in fact move around erratically in solution or in a colloid, and so the Brownian motion is the erratic motion of particles. And the way they determined that, or the way Robert Brown determined that, was from the observation of the scintillation of the particles. Simply meaning, it's almost like you have a sparkling dress or something like that, or a diamond ring, where as it moves in various ways in the light, it will appear to sparkle. That's that scintillating effect. Well, the reason why the colloids are going to be scintillating is because as the particles get bounced around, their orientation continually moves around, and then that's going to scatter the light in slightly different ways. So you're basically going to be seeing the light flash at you for a split second, and then away from you for a split second, and back and forth, and that gives it that scintillating effect. That Brownian motion is what causes that erratic movement of particles. You can also see Brownian motion if you mix, say, if you have a beaker of water, all right, and you put a few drops of, say, food coloring in there, you'll see the food coloring getting mixed around by the motion of the particles. All right, and so that was observed first inside of a colloid. Now, in terms of coagulation, now when we say the term coagulation, most of you will think about blood coagulating on your skin so that it actually stops the bleeding if you have a cut. Well, in terms of colloids do not coagulate. What happens, and part of the reason why they stay suspended, is that particles will take on a charge inside of the colloid. So let me draw a picture of this one as well. So if this is your colloid, the particles themselves will take on a charge. Now, we'll make all these positives, but they could be negatives. Now, all of the particles in a sample will be the same charge. It just depends on the nature of the colloid. So if the colloid is negative, they're all negative in that colloid. If they're positive, they're all positive in that particular system. But because these things take on charges by picking up a charge from the other particles within the system, they're all going to repel one another. And this repulsion helps to keep these things from settling out. So these things don't want to settle to the bottom because they're pushing away from each other. Now, if you want a colloid to actually settle out, you have to disrupt this system, and so you can settle or separate a colloid by disrupting the system by adding particles of opposite charge. Because if in this case you introduce, say, negative particles, well, this negative particle is going to attract this one and this one and this one and any of the other ones in the immediate area, and so it's going to start clumping the colloid particles, and those will eventually settle to the bottom. All right. So just to summarize what we've talked about in this chapter, solutions. Solutions have ions or atoms or small molecules less than a nanometer. They do not scatter light. They do not settle out based on gravity to the bottom. You cannot filter these particles out, and it's considered a homogeneous mixture because you only see one phase. On the other hand, colloidal systems are medium-sized particles. They don't settle to the bottom, but they do exhibit the Tyndall effect. They are heterogeneous systems. A suspension has larger particles that will settle to the bottom. They still will scatter light, so they do exhibit the Tyndall effect, and we do call them a heterogeneous mixture, or a heterogeneous system anyway. All right? That concludes Chapter 15.